Assalamu alaikum everyone. This is the power transmission course, and in the last lecture we were studying the string insulators, and we have studied about the string efficiency and also solved some examples for that. In today's lecture we are going to talk about sag of the conductors, and I have already explained a little bit about sag. So there are two terms that we have to define. The first one is span and the second one is sag. So span is actually a distance between the two consecutive towers. So it is a horizontal distance between the two consecutive towers. And for sag, it is a difference between the lowest conductor point, which is this one, and support points. And support points are actually the points where the conductor is attached to the supports, which are actually tower. So the distance between the lowest point of the conductor and the line, which is actually the horizontal line connecting the top of the towers where the conductors are attached. So this vertical length is known as sag. So now this particular curve, this is the shape of catenary, and this is formed whenever we have a conductor that is hanging between two supports. So if we have a conductor which is very tightly stretched, means the tension in the conductor is very high, then the sag is very small, and if the tension is small, then the sag will be larger, something like that. So tension and sag, these are inversely proportional. So in case we have a small sag, then the curve will be considered as parabola, or we can just approximate it as a parabola, and we can use the formulas for the parabola that already exist, and we don't have to derive any new formula. But in case we have sag which is less than 6% of the span, for example, if we have span which is equal to length L and sag is only 6% of the total length L, then the error is 0.5% if we are using the parabolic equations. But if the sag is greater than 6%, for example from 6% to 10%, then the error will be around 10%. So we cannot use parabolic equations if the sag is more than 6%. So for that case we have to derive the formulas for the curve which is in the shape of catenary. Now there are few points before going on into the derivation that we should know. The first one is that the tension at any point of the conductor act tangentially. For example, we have a point O, this is the lowest point of the conductor, and if I have to find the tension at this point, so it will be tangent to point O, right? And the second point is that the horizontal component of the tension is constant throughout the conductor. So whether it is at point O, at point B, at some point, for example P, the horizontal component will be constant, and the tension at the supports, for the tension at the supports means the T value where the conductor is attached with the tower, it is actually equal to the horizontal tension. So T is the tension at the point of connection between conductor and towers, and T naught is the tension at point O, which is the horizontal tension. So the tension at the support approximately equals to the horizontal tension. So these are the few points that we have to keep in mind. Just to revise, span is actually the distance between the two consecutive towers, and the sag is the distance between the top of the tower where the conductor is attached and the minimum point of the conductor. So now if we have to define the sag and tension relationship, they are actually inversely proportional. And what we want, we actually need sag to be minimum and tension also should be minimized, right? So if the sag is minimum, it means that tension is larger because the conductor will be of this shape, and if the sag is minimum, the conductor material used will be lesser than the one that has larger sag. And if we have a larger sag, then the height of the tower should be greater as well, right? Because there should be a specific amount of ground clearance, and ground clearance is actually the distance between the lowest point of the conductor and the ground. So what we want sag to be minimum, but not that small that the tension will be very high, and not that large that the ground clearance will be smaller. And the second point was that we need tension to be minimized. Why? Because if the tension in the conductor will be large, then there is a chance that the conductor will break. And if the tension is large, then the supports, which are actually tower, they should be strong enough to support that particular conductor. So in both the cases, we have to compromise between one of the two quantities, because sag and tension, they are inversely related. So if sag will be larger, then the tension will be smaller, but if tension will be larger, then the sag will be smaller. So we have to compromise between these two quantities. Now we will be moving on towards the calculation of the sag. We are given with two towers. We have tower A and tower B. We have a conductor in between these two towers. The span of the conductor, it is actually equal to length L, and we have the minimum point of the conductor at point O, which is at the center of the transmission line, right? So we have two equal parts, L by 2 on one side of the lowest point of the conductor and L by 2 on the other side. And then we have tension T, that is represented at point O, which is the lowest point of the conductor. And then there is a weight W, that is defined as weight per unit length of the conductor, right? So what we want to calculate the sag, and sag is this height. So sag is the difference between the point that connects the support points where the conductor is attached and the lowest point of the conductor. So what we want to calculate the value of sag, and to start with the derivation, I will consider a point P, which is at some height y from the point O, as well as at a horizontal distance x, right? What we assume that is this particular curve is so small that this distance OP is actually the horizontal projection of the actual curve OP. So what we actually assume that the curve OP is small. So if this curve OP is small, so we can assume that this is actually a straight line. So it is equal to the horizontal projection of OP, horizontal projection of OP, which is a straight line. So we can say that OP is actually equal to X, which is the horizontal projection of OP. So now if you look at this particular curve OP, there are two forces that are acting. One is the weight Wx, and the other one is tension. So there are two forces that are acting on that particular part of the conductor, which is OP. One is weight Wx. We have a portion of the conductor whose length is x, so I am taking weight is equal to Wx, and this particular weight, it is acting at a distance x by 2, at a distance x by 2. And then we have another force, that is tension T, acting at O. So now we have defined two forces. One is the weight, which is acting vertically downward, and then there is a tension which is acting tangentially at point O. So now what we want to calculate the moment of force. Now what is moment of force? It is actually the tendency of a body to rotate around a fixed axis, right? So if I'll write it down, tendency of body to rotate around a fixed point. So that is known as moment of force. And if I have to define its formula, so moment is actually equal to force into distance. And this distance is actually from origin, from some focal point, right? So in this particular example, if we have a weight which is acting downward, so it is trying to rotate the transmission line in the clockwise direction, right? And the distance from the origin, if I will assume this O is origin, will be x by 2. So what is the moment of force? It is just the multiplication of force, which is Wx, which is the weight of that particular part of the conductor, into the distance from the origin. So this is one force, and if I have to find the other force, which is torque, so if this is point P, the torque at point P will be in this direction, and if I will extend this to this point, I have to calculate the moment of force with respect to the origin. So if I will extend this till this point, so the distance between the point where the force is being acting and the origin is actually this one, which is y. So now in case of tension, so if there is a force that is acting at this point, and it, for example, actually the force is acting at point P, so I'm just explaining it here to make it easier to understand. So if the force is acting at this point and it is in the direction of this particular arrow, then what the force is trying to do, it is trying to rotate the transmission line in the anti-clockwise direction, right? So now if we want this whole transmission system to be in equilibrium, we should have this force that is acting anti-clockwise and the other force which is acting clockwise equal. So the first force was torque. For torque at O, we have the value T into what is the vertical distance? Y. And the second force was weight, right? So this is acting at the center of the portion of the conductor that we considered. So the actual weight is Wx, weight per unit length. So the total conductor length that we are considering is x. So we have multiplied weight with x into at what point from the origin it is being acting, it is x by 2, right? So we have two forces, one that is acting anti-clockwise and the second one is weight which is acting clockwise. So now if we want the system to be in equilibrium, so these two particular forces should be equal. So we have Ty is equal to Wx into x by 2, right? So after solving, it will become Ty is equal to omega x square over 2. Now what we wanted to calculate, in the start of the derivation we actually wanted to calculate the sag, right? And sag is actually the vertical distance which is denoted by y. So we can say that y is actually equal to sag. So if y is equal to sag, so this formula will become S is equal to Wx square over 2t. So this is the generic formula for all the cases for the transmission line where we have to calculate the sag. Now in this particular case where the supports are actually having the same height, if I have to calculate the sag, for this particular case, then we already know that y is equal to s, which is actually sag, and x is, if I have to define the x, it is the horizontal distance at which the conductor has the minimum height. Right? So this is actually the distance x from the tower to the point where the conductor has the minimum height. And in this particular derivation we have actually considered the point P. For that it was x, but in the actual case this x is the horizontal distance between the support point where the conductor is attached with the tower and the point where the conductor has the lowest ground clearance, and the vertical distance, it is actually the sag. So now we know the formula, we can replace the value of x and y with s, which is equal to sag, and x is actually the length of the line. So now we know the formula, ty is equal to omega x square over 2, and y in this case is equal to s, and for the value of x it is L by 2 square divided by 2, right? If the total length is L and the lowest point is at a distance L by 2 from the particular support or tower, then we can replace x equal to L by 2. So after solving, it will become s is equal to WL square over 8t. So this is the formula for sag calculation when we have towers of same height, right? And we also have the generic formula, which is for all the cases. So what I have done, I have actually found out the two forces. One is the weight that is actually acting downward, and the second one is the torque that is actually acting in the anti-clockwise direction. So we have one force in anti-clockwise direction, the other one in the clockwise direction. So if we have to keep the transmission line in equilibrium, so what we have to do, we have to equate it and assume that if they are equal, then the transmission line will be in equilibrium, right? And from there we have calculated the formula for sag. This one was the generic formula, and for this particular case where the towers actually have the same height, the sag is actually WL square over 8t, where W is the weight per unit length and L is the span of the line, T is the tension.